Okay, so we are continuing on the reactions of alcohols, and we've done the acid-base chemistry in class already, and we were starting to look at the conversion to good SN substrates. And just to recap, although one would expect by looking at the structure of an alcohol, the fact that the alpha carbon is electrophilic, or this has a delta plus charge, you'd expect that alcohols would be good electrophiles, but the reaction with, say, cyanide does not go because the product of the reaction includes hydroxide, which is a strong base. And so a weak base cannot make a strong base, and so this reaction is forbidden. So alcohols, in fact, are terrible electrophiles. It is possible to convert alcohols, however, into good electrophiles, particularly for SN reactions. And we had met two ways of doing this so far in class. One was very crude, but certainly very effective, which is simply to protonate the alcohol. And we saw that if I took an alcohol and I treat it with an acid, and we had been doing a lot of these in curved arrows over the course of the last few lectures, that you would convert the alcohol into the oxonium ion. There would be a loss of water, which may or may not involve some sort of a rearrangement of the R group, right? So, for example, if loss of water directly would have led to a primary carbocation, that couldn't happen. So there may be an intramolecular hydride shift or methide shift or alkanide shift, but you'd eventually get maybe R plus perhaps if it's a carbocation on your product. So what we've done is we've converted the OH, which is a bad leaving group, into H2O. And it may well be, for example, that the SN reaction we get may involve SN1, as I have it here, or it could well be that some nucleophile, right, may attack the species before the water leaves, right? So I can have the nucleophile attack here and have water come off, and then get an SN2 reaction that will give rise to R-nuc. But certainly protonating the alcohol is a really good way of converting the alcohol into a good substrate for an SN reaction. We saw as well that I can convert the alcohol into a haloalkene, which is really by far perhaps the most common way of activating alcohols to SN reactions. We pointed out in class that there are a number of very commonly used alkylating agents, halogenating agents. And they would include the phosphorus halides, so PXN, where N is equal to 3 or 5. And then there's SOX2, and then there's SO2X2. And we had drawn mechanisms for how this reaction goes and how that reaction goes. And then another one is use of cold concentrated HX. And we spent quite a few minutes talking about the logic behind the use of cold conditions and concentrated conditions. And the idea was you were trying to minimize the amount of competitive E reaction, and that made perfect sense. One of the other ways in which you can convert alcohols into good substrates is by reacting the alcohol with what I'll write as Z, SO2Cl. And that converts the alcohol into what's called a sulfonate ester. Z could be really any number of species. By far the most common versions of Z are methyl, trifluoromethyl, and then a paratolulyl group. Right? So you've got the methyl group in the P position on the benzene ring. When Z is methyl, then this compound is called mesyl chloride. When it's trifluoromethyl, it's called triflyl chloride. And when it's p-tolulyl, it's called p-tolulyl chloride. When we make the ester, this is called a sulfonate ester. Sulfonate ester. And of course, it's an ester because it basically is the alcohol derivative of a sulfonic acid, right? When Z is methyl, then the ester is called a mesylate ester. Then, when it's trifluoromethyl, it's called a triflate ester. And this is called a tosylate ester. And if you want to be anal, it's the p-tosylate ester. The way this reaction goes, in fact, is actually a mirror of the way the reaction goes with the thionyl chloride. And we talked about this in class as well. You can imagine how this will happen. The alcohol will attack the sulfonate group, right? And we have cleavage of the pi bond, and that will give rise to ROH, S double bond O, O minus, Cl, and Z, plus some base will come in, suck off the proton. I'll have this come back, kick out my chloride, and that will give rise to RO, S double bond O, Z. This really is a mirror image of the reaction we'd seen earlier. I will point out, and I didn't mention this in class before, but I will point it out now. If you remember, when we began looking at the reactions of alcohols, we made the point that if you look at an alcohol, and I made the joke that one of my professors had called this geochemistry. If you look at an alcohol, you'd expect alcohols to be electrophilic because of the delta plus charge. That's not observed because it's not just about how positive the carbon is, but about the propensity of the leaving group to depart. And in the particular case of hydroxide, which is a terrible leaving group, it doesn't come off very easily. And as a result, alcohols are poor electrophiles. But the other properties of alcohols we expected would have been basicity, which we saw. We saw alcohols could act as bases, reacting with both protic acids, right? For example, case in point, or with Lewis acids. We saw that alcohols could be acids, reacting with bases like hydroxide and H- and so on. But we also saw alcohols could be nucleophilic. And the examples of nucleophilic alcohols, we've actually seen some of those already, right? We looked at the reaction, for example, of alcohols with PX3, right? We did this in class with alcohols attacking the alcohols attacking the PX3 or the sulfuryl chloride, right? This is the alcohol attacking here by virtue of its lone pair of electrons, right? And therefore, that is evidence of the alcohol's nucleophilicity, right? This is the alcohol acting as a nucleophile, and that's what we predicted based upon the presence of a lone pair of electrons on the O. Attacking the sulfonyl chloride, we also saw that before as well, with attacks of thionyl chloride. And now this is another example when we convert the alcohol to the sulfonate ester. That's another example, another illustration of alcohols acting as nucleophiles. So really then, the properties of alcohols that we had expected, all except for the electrophilic character, which really is not the fault of the R group, but the fault of the leaving group, all of the properties we've actually seen manifested in the chemistry of the alcohol. There is a point that needs to be made, which is that sulfonates, sulfonate esters, are excellent substrates for SN reactions. But it tend to be substrates for SN1 reactions because this group is an exceedingly good leaving group to generate carbocations and a wonderfully stabilized counterion, right? So this species is beautifully resonance stabilized over both of these sulfonyl groups. So what you get is 3 equivalent resonance forms where the negative charge is supported on an O, right? And you remember then, when you support the negative charge on an O, those are particularly stable. And the more equivalent resonance forms that you can draw, the more stable is the species. And in particular, if you take Z and you make Z equals CF3, then this group, this triflate group as it's called, really represents the world's very best charged leaving group. The triflate anion is the world's best charged leaving group. This is called the triflate group, right? And this is really, really, really good. So the world's best leaving group is nitrogen, right? Water is actually a very good leaving group as well, but the world's best charged leaving group is triflate. And so if I want a reaction to go via SN1 or E1, if I want a unimolecular reaction, chances are I'll conduct the reaction using a triflate, right? Because they tend to promote unimolecular reactions. Okay, so that would end the methods of converting alcohols into good substrates for SN1 reactions. So the crude method, which was protonation, we could also convert the alcohol into a haloalkane, and there was a myriad of halogenating agents, and you are responsible for the mechanisms we've covered in class. Also, we could convert alcohols into triflate esters, but we would really do that if our intent is to carry out unimolecular chemistry, in particular SN1 chemistry. Okay, so there are other reactions of alcohols that we want to look at, and we're going to look at what's called silylation, right? We're going to look at silylation of alcohols. I'm sorry, I'm not numbering these. I think the first was acid-base. The second was conversion into good SN substrates. And so silylation would be 3. And what we do for silylation reactions is we treat the alcohol with, I'm going to write it as TMSCl in the presence of pyridine. So let's see what these things are. TMSCl is an acronym for trimethylsilyl chloride, which is this compound, right? So it's trimethyl, right? So there's the methyl groups here, right? So it's trimethylsilyl chloride. PY is the accepted abbreviation for this compound, which is pyridine, right? So PY is pyridine. So pyridine is actually very much like benzene, where an N has replaced one of the carbons, right? In fact, that's exactly what it is. In fact, in the bad old days, pyridine was called azabenzene, right? Aza is one of the accepted prefixes for nitrogen. So am and aza are the accepted prefixes for nitrogen, or prefaces for nitrogen. So if I treat the alcohol with trimethylsilyl chloride and pyridine, what I end up with is this compound. And I'll write it like this. I'll write it 2 ways, right? So I can get this compound, which I can also write as ROTMS, right? RO trimethylsilyl. And you'll want to get fairly familiar with this lingo because it's used fairly often. Let's get a sense of how this reaction occurs. Well, this is another illustration of alcohols acting as nucleophiles. And what you get is the alcohol attacking the trimethylsilyl chloride, kicking out the chloride, and generating the corresponding oxonium ion, right? And you lose chloride. Another illustration of alcohols as nucleophiles. Some base, almost surely the alcohol, some base, and this is why we use pyridine, right? So I shouldn't say some base, the base is pyridine. Pyridine comes in and pulls off the proton, and that generates, I'm going to run out of room, and that generates this species. That generates this species, right? So I lose protonated pyridine, which is the pyridinium ion, and I'll have ROTMS. So what is the role of pyridine? Pyridine serves 2 roles in this reaction. One, it's the solvent, right? And it's actually a really good solvent because pyridine is relatively polar, as you can imagine, right? It's got a pretty decent dipole moment. It's hydrogen bonding, So it will hydrogen bond to the alcohol. And of course, because it's polar, it will dissolve the trimethyl silyl chloride. It will dissolve the ether. So it's a wonderful solvent from that perspective. Pyridine stinks to high heavens, but it's a really good solvent. It has the additional advantage of being basic and weakly basic. So pyridine is often used as a non-nucleophilic weak base. So if I just want something to sop up, right, just to soak up acidic protons, pyridine is actually fantastic. It's not basic enough, it's not nucleophilic enough to carry out any chemistry, but it will function as a base. It's not a strong enough base to do an E reaction, for example. It's nowhere near the category of hydroxide or God forbid, hydride. It's a very weak base. And if I have a particularly acidic proton, like one of these, pyridine is really good at sucking those up. So it really is just a proton sponge, right, to soak up particularly active protons. So it's the best of both worlds here. It's a solvent, which will dissolve my starting materials and my products, so I can get chemistry in solution. And it allows my reaction to go forward by picking up the acidic proton. Okay, there's something interesting in this reaction. You notice the way I've drawn this mechanism is the alcohol is attacking what really is a tertiary substrate. And we know from SN2 chemistry back in 301 that reactions, that SN2 reactions on tertiary substrates is forbidden. Right? Tertiary substrates are too sterically crowded. And if you remember from your 301, there are two sorts of species upon which SN2 reactions are not possible. Tertiary substrates and substrates where the alpha carbon is adjacent to a quaternary site. And so SN2 should not be possible on that species. Well, it turns out that boundary condition actually does not apply in our case, and here's the reason. So if I imagine so certainly, for example, if my substrate were T-butyl chloride, right? If I were dealing with T-butyl chloride, then I would not have gotten this reaction, right? The alcohol would be incapable of carrying out this reaction, right? So I wouldn't get that. But I am getting it here with a silyl chloride, and the question is why? And the answer is, if you imagine this to be the size of a carbon atom, and so here's the bond to the chlorine, well then, if I have attached to my carbon 3 methyls, well, a methyl is a little bit bigger than a carbon. And then a methyl is a little bit bigger than a carbon. And a methyl is a little bit bigger than a carbon. Right? Therefore, a nucleophile would find it impossible to find its way in and do chemistry. So absolutely, SN2 reactions on a tertiary substrate is forbidden. But I'm not dealing with carbon, right? I'm dealing with TMSCl, and silicon is a much bigger atom than carbon. So yes, I still have my methyl group here, and I still have my methyl group here, and I still have my methyl group here. But my goodness, there's tons of room for a nucleophile to approach. There's a huge window for backside attack. So because silicon is a bigger atom than carbon, the silicon atom is actually open, it's sterically open to nucleophilic attack. In fact, if I went below silicon to say germanium, which is about that big, SN2 reactions on that are exceedingly easy because if I have an R group here, and another R group here, and an R group here, there's tons and tons of room for my nucleophile to approach. So sure enough, SN2 reactions on tertiary carbon substrates are impossible. But SN2 reactions on tertiary silyl, tertiary germanyl, tertiary plumbyl, and so on, those are entirely possible. However, and let me just put a caveat, if you asked in an exam, is SN2 possible on a tertiary substrate? The answer would be no, because you would make the assumption, unless told otherwise, tertiary substrate means carbon being attacked, right? So it's purely organic. It doesn't have a silicon or a germanium in it. This compound is an ether, right? Because silicon is 1 below carbon in group 4, right? And so this compound is analogous to an ROR, right? It's a carbon O silicon, kind of like a carbon O carbon. And so this is referred to as an alkyl silyl ether, right? It's called an alkyl silyl ether. Ethers, of course, would come in multiple flavors, right? There are dialkyl ethers. Those are the ones we're typically accustomed to, the ROR. There are alkyl silyl ethers, and there's no reason why we couldn't have a silyl ether, right? A silyl ether, so R3Si. Okay, so why are we studying this silylation reaction? And certainly it's interesting, right, from the perspective that it's another illustration of alcohols acting as nucleophiles, and that's good. It's an illustration of a new class of compounds, right, which is the alkyl silyl ethers. It illustrates the use of pyridine, the rather clever use of pyridine as both a solvent and as a proton sponge. And that really, in and of itself, would be good reasons for studying the silylation reaction. But there's another aspect to silylation that is really pivotal in organic chemistry. And I'll set it up this way. So let's imagine I asked you to carry out this reaction. Let's say I want you to convert this compound into maybe, say, this compound. Right? I want to convert this compound into this one. So I would expect you to say, well, look, I mean, all I've done, I haven't messed with this part of the molecule. What I basically did is I converted CCl into C-phenyl. So basically, I'm bringing in an alkyl group. In this case, it's an aromatic group. But I can see myself saying, well, that's simply a coupling reaction. So I'm going to use lithium diphenyl cuprate, right? So I'm going to do the Corey-Poisson-Whitehead-House reaction. And I would expect the phenyl group to come in, carry out my attack, and give rise to my product, right? And that would seem to be a reasonable thing to do. It turns out, though, if I carry out this reaction, I'm not going to get any of this product, none. All I will succeed in making would be this compound. Now, there are two kinds of synthetic errors that you can make in a lab. One is that I'm trying to mix A and B in an attempt to make C. And one option is I mix A and B and nothing happens. I get no C, I get nothing. I just have unreacted A and B. Well, that's bad, but it's not horrible, because at least I can go back and isolate pure A, isolate pure B, and try again, right? Try it in some other sequence. I would have wasted time, I would have wasted solvent, I would have wasted some resources, but I still have my starter materials. So that's bad. What is worse is if I mix A and B in an attempt to make C, I don't get any C, but I make D. That is horrible, because now not only have I failed in making C, but I've used up my reagents, right? And I've spent time and manpower and whatever. This is a very bad thing. This is what people get pink slips for, right? So the question is, how is it we don't get this product, and why on earth are we getting this one? And the reason is actually fairly simple. What you want to remember is something we've preached really from the beginning, which is that the fastest reaction in organic chemistry is proton transfer, particularly when it involves heteroatoms. So phenyl minus, and of course it's not really phenyl minus, right? It's actually phenyl bound to the copper, but for all intents and purposes, we'll treat it as phenyl minus. Phenyl minus sees two targets in this molecule. It can carry out the SN2 reaction on the carbon-chlorine system, or there is the option of carrying out a reaction on the OH. In other words, I could have phenyl minus pull off the proton and make O minus. And that reaction would be an acid-base reaction that would be encouraged, because O minus would be a more stable base than phenyl minus, right? Because the negative charge is supporting the O. But proton transfer is literally millions of times faster than an SN2 reaction. SN2 reactions are behemoths. SN2 and E2 reactions are behemoths of all of the organic reactions. They are the slowest of the lot. So when I treat this compound with lithium diphenyl cuprate, none of this happens. Instead, this is what occurs. And I would have then set loose into my molecule, intramolecularly, I would have set loose a good nucleophile in a molecule that has a good electrophilic site. So the head simply bites the tail, right? The head simply bites the tail, and I get an intramolecular reaction that kicks out chloride and generates this product. Okay? Now, I'm going to make 2 points. Point 1, I will reiterate that when a molecule is polyfunctional, see, this compound it's an alcohol function, it has a haloalkane function. When you are doing chemistry on a molecule that has a single functional group, you don't really have a huge issue when you're doing interconversions. But when a molecule has more than one functional group, you have to be very careful that the reagent that you are subjecting the molecule to localizes the chemistry on the site you want it to carry out chemistry on. Because if your reagent can carry out chemistry at both sites, then you're going to have a problem because you now have to figure out the relative rates of the reaction, right? And if it is much, much faster at the site you want, well, great. But if it is much, much slower at the site you want, that's a problem. So when you're dealing with molecules that are polyfunctional, you've got to be very, very careful in terms of your use of reagents and ensuring how the reagent behaves, ensuring that you understand how the reagent behaves at each of the functional groups. Hitherto, most of the reactions we've been dealing with are monofunctional substrates. In the real world, your compound will have 8, 10, 12, 15, sometimes even more functional groups. And it's a real issue to try to steer the reagent at a particular site and not at another one. So suppose I wanted to make this compound. Suppose this compound was critical and I had access to this one in my lab and the cuprate. How would I do the reaction, or am I doomed never to be able to make that compound? And the answer is we're organic chemists, right? We solve problems. So here is what we would do. Right, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So here's what we would do. I would recognize that the problem here is the acidity of the H, right? That really is the issue, right? That the phenyl group, when confronted with an OH, will go after it. If the OH were not there, it only has one target then. It would go after that. Okay? So my job then is to protect the OH group, to move it, to mask it. So I'm going to treat this compound with TMSCl in pyridine. And what will that do? That will convert my chloroalcohol into this compound. Right? That's the stuff that we were just doing here. Convert the alcohol into the alkyl silyl ether. Right? So I'm going to convert my chloroalcohol into the chloroalkyl silyl ether. Now, why would I do that? I do that because ethers, even though they are kindred in a way to alcohols, are very different from alcohols. How so? Here is my alcohol, here is my ether. And whether this is R or silyl, it doesn't matter, right? It's an ether. You remember in class we were talking about, we said, so with acids and bases. So we said that alcohols, by virtue of the lone pair of electrons on them, can react as bases. Therefore, alcohols will react with acids, right? Alcohols are basic by virtue of the lone pair. They react with acids. So I'm going to ask, are alcohols acid labile? And the answer is yes, because if the compound is basic, it will react with acids. It will react under acidic conditions. It would be reactive under acidic conditions. It would be labile under acidic conditions. It is acid labile. Are alcohols base labile? Are alcohols base labile? Well, let's see. You will be base labile if you react with bases. You will react with bases if you are acidic. Are alcohols acidic? Absolutely. They have an acidic H. Therefore, alcohols are both acid labile and base labile. They will react with bases, which was the problem here, right? It's reacting with a base. Well, what about ethers? Are ethers acid labile? In other words, if I treat an ether with an acid, will I get chemistry? Will the ether react with acids? Is the ether basic? Absolutely. It has lone pairs. So ethers are acid labile. And by the way, we did this in class the other day. We showed that I can take an ether, treat it with an acid, right? And that would generate ROR, H+, and then depending upon what the R groups were, the reaction, for example, could be SN2 at this point, and I'd make one alcohol, right? I'd make ROH, and then I'd make ROH2+, and then another water would come in, suck off the proton, and I'd make my second ROH. So ethers are certainly acid labile, right? In fact, I can hydrolyze the ether to make an alcohol. We talked about that in preparation of alcohols. But are ethers base labile? Will ethers react with bases? Can ethers react under basic conditions? Well, they would if they had an acidic H, but they don't. Therefore, ethers are not base labile. In fact, what we say is that ethers are rock stable. We say ethers are rock stable in base. So basic conditions do not bother ethers. And why is that important? That's important because once I have made my alkyl silyl ether, right, my derivative of the alcohol, I can now treat this molecule with lithium diphenyl cuprate. And unlike the alcohol that provided it two targets, this is the one it favored, the ether provides it with one target, just that one. And so it has no choice but to go after this site and give you this compound. So I can convert my alcohol to my ether, carry out chemistry under basic conditions with impunity, recognizing that nothing will happen at this site. Well, this is fantastic, this is great, except that that's not what I wanted to make. What I wanted to make was the corresponding alcohol. So what would I do? Well, ethers are acid labile. So if I treat this compound with aqueous acid, what's going to happen? It'll do what ethers do and generate the pair of alcohols. So what I would get would be pH, OH, and then what basically is this compound. It'll be TMS-OH, but I'll write it like this, SIME3. It's called trimethylsilanol. What's really neat is I can take the trimethylsilanol later on, react with PCl5 or something, and make back TMSCl that I can use for some other reaction later on. But I have now converted my chloroalcohol through the ether into my substituted alcohol, which was my intent. This sequence in which we mask the OH group as the ether, carry out our chemistry under basic conditions, and then unmask the ether as the alcohol is called protection, deprotection. This is called a protection, deprotection cycle. In the bad old days, it was called masking, unmasking. But nowadays it's called using a protection, deprotection cycle. It is a critical tool in carrying out chemistry on polyfunctional compounds. And in fact, as it turns out, for every functional group known to man, there is a protecting group that you can use. right, which will mask it, allow you to carry out chemistry, and then you can unmask the functional group. There is another way in which we can mask the mask the alcohol. So instead of using TMSCl, right, what is often done as well is I can use isobutylene and HCl. And what happens is the isobutylene is attacked by HCl and makes the carbocation. The alcohol attacks the carbocation, and you end up making this compound. You make the T-butyl ether. So that's another way of, and of course it's an ether, so it's stable under basic conditions and it's acid labile. So this is just a companion method together with the silylation. It's a companion method for generating a protecting group for my alcohol. And if you're asked which method is better, the answer is really neither one. I've used them both. Both work very, very nicely. I mean, if I had a preference, I'd probably do the second one. Isobutylene is a gas, and it does have a few little issues. Pyridine stinks to high heavens, and that's another issue, plus pyridine is somewhat toxic. But, you know, both work quite well. You do want to watch out, by the way, for cases where the molecule is polyfunctional, because that would become an issue down the road. Because almost surely in one of your questions on an exam, you'll be given a case where you have to navigate around a polyfunctional molecule. Okay. We will look now at oxidation of alcohols, and I will need to get a new page, I think. Maybe I can do that here. I'm sorry, excuse me. So oxidation of alcohols. Now, we've met some of this already, in fact. You will remember we said that what makes a compound, at least in the oxygen series, oxidizable is the presence of either a carbonyl H, right? This is a carbonyl H, or the presence of a carbonyl or carbonyl H, right? So if a compound has either one of these, it will be oxidizable. We saw that I can take methanol, which has 3 carbonyl H's. I can oxidize that into methanol, and that's an oxidation because, on the one hand, I've lost H's, but more importantly, I have gained a bond to a heteroatom. So that's a 2-electron oxidation. I can oxidize methanol to methanoic acid. That's also an oxidation because I've gained a bond to a heteroatom. I can oxidize methanoic acid to carbonic acid. And of course, carbonic acid, being a gem diol, is in equilibrium, with carbon dioxide, right? It will lose water to form carbon dioxide, okay? If I have a primary alcohol, primary alcohols are oxidizable, and they will go into the aldehyde. The aldehyde can be oxidized into carboxylic acid, and there it will stop, because at this point we are devoid of either a carbonyl H or a carbonyl H. If I had a secondary alcohol, they are oxidizable into the corresponding ketone, and there we stop because now we're devoid of carbonyl or carbonyl H's. And certainly tertiary alcohols are not oxidizable, right? I can't oxidize tertiary alcohols, right? So I would say of all my alcohols, tertiary alcohols are not oxidizable, but in other words, tertiary alcohols are non-reducing, right? They don't reduce the oxidizing agent. But certainly methanol, which is a one-member class, and primary alcohols and secondary alcohols, those are oxidizable. Okay, we are interested in knowing which reagents can I use to carry out an oxidation. So suppose I have a primary alcohol, and I'm interested in converting the primary alcohol to an aldehyde. or perhaps the aldehyde into carboxylic acid. Maybe I might have a secondary alcohol, in which case I want to maybe convert that into the ketone. How do I do those? Now, I will remind you that just a little while ago, we did the backwards reaction. We said I can convert the carboxylic acid all the way down to the alcohol using lithium aluminum hydride followed by water. Or I can convert the carboxylic acid to the aldehyde using lithium aluminum tris T-butoxyhydride followed by water. I could take the aldehyde down to the alcohol. So let's use LAH. Curious. So LAH 1, water 2. I can take the aldehyde down to the alcohol using either sodium borohydride, aqueous, or LAH, lithium aluminum hydride, followed by water. I'm going to rewrite this here just in case it's not very clear. So LAH 1, 2, water. So, and again, if I wanted to go from the ketone to the secondary alcohol, this would be sodium borohydride, aqueous, or lithium aluminum hydride followed by water. Okay, great. So I know how to reduce by 2 electrons, by 2 electrons, or by 4 electrons. And we already spent some time looking at why the aluminum hydride is the only one capable of doing a 4-electron reduction, right? Why the aluminum hydride is the big gun. Borohydride and the tris T-butoxy aluminum hydride are not quite as potent, and we spent a lot of time discussing that already, so I won't go over that. What we want to do now really is the opposite thing, right? We want to, instead of doing the reductions to make the alcohols, we want to oxidize the alcohols up. So how would I go from the alcohol to the aldehyde and stop? How would I go from the aldehyde to the acid? And how could I go from the alcohol all the way to the carboxylic acid? Right? And it turns out that there are companion or mirroring sort of reagents. So you've met many of these reagents already. You've met potassium permanganate. So acidified permanganate is the equivalent, is the oxidizing equivalent of lithium aluminum hydride as a reductant. In other words, it's the big gun. Permanganate will oxidize anybody who can be oxidized. So if you have a carbonyl H or a carbonyl H, permanganate will oxidize you. Another one that can do that is acidified dichromate. Acidified dichromate has a name, odd. Acidified dichromate has a particular name. It's called Jones reagent. Right? It's called Jones reagent. So if I wanted to go from the primary alcohol to the carboxylic acid, I'd use acidified permanganate or Jones reagent. Okay? If I wanted to go from the secondary alcohol to the ketone, I would use acidified permanganate, or I could use Jones reagent. Right? They will oxidize this to the ketone and stop because the ketone is not further oxidizable. Ketones don't have, they're devoid of carbonyl and carbonyl H's. Okay. Now, if I wanted to oxidize the aldehyde to the carboxylic acid, I could use Jones reagent, I could use acidified permanganate, or I could use Jones reagent, because this will oxidize everybody that can be oxidized. Great. Well, what if I wanted to go from the primary alcohol to the aldehyde? Couldn't use Jones, because that's going to go all the way. Couldn't use permanganate, because that's going to go all the way. There are two reagents that are commonly used. One is called PCC, which is used in methylene chloride, and the other one is called Swern oxidation. We're not going to get into great detail of what these things are. PCC is an acronym for pyridinium chlorochromate. And basically what it is you take pyridine and HCl and CrO3. So you dissolve chromium 6 oxide or chromium trioxide and pyridine in HCl. You make that mixture, and it's called pyridinium chlorochromate. Pyridinium chlorochromate, like Jones reagent, actually is chromium 6, but it will not oxidize the alcohol all the way into carboxylic acid. It will stop at the aldehyde level. So I can actually use the PCC in methylene chloride to carry out the oxidation of the alcohol to the ketone, or I could use Swern. Oh, by the way, Swern is a reagent that is a sequence that involves this compound, which is called oxalyl chloride. Right, and you are not required to know the mechanisms for any of these oxidations, right? Just the reagent list. Well, it turns out that in addition to using Jones or permanganate to oxidize the aldehyde to the carboxylic acid, there is another set of reagents we can use, and these are a little more esoteric. They involve using a metal diamino cation, where the metal is either copper 1, or silver. So the way you make this is, for example, let's see you want the silver compound. You would take, for example, silver nitrate, which is water soluble. You would add to it aqueous ammonia until you get a precipitate. Then you would keep adding ammonia until the precipitate dissolves. And at that point, this is what you'd have. You'd have the silver cation complexed to 2 neutral ammonia molecules. And that's PCs, a complex called a diamino silver 1 cation. This is the diamino silver 1 cation. Okay? Now, when we're using this species, this is called Tollens reagent. Okay? When we use the copper species, so the diamino copper 1 species, it turns out there are 2 different names for it. And it depends on who the counter ion is. The counter ion is typically tartarate or citrate. And that gives rise to Benedict's solution or Fehling's solution. Right? The counter ion is irrelevant. And Tollens reagent, Benedict's solution, Fehling's solution act in exactly the same way. They carry out exactly the same chemistry. Fundamentally, what they do is you would use, say, 2 silver pluses. You would react that with your aldehyde, and the 2 silver pluses will form silver 0. They will gain 2 electrons. Those 2 electrons are the ones the aldehyde loses in becoming a carboxylic acid. Because remember, here I've got 2 bonds to heteroatoms. Here I've got 3. So that's a 2 electron loss. Those 2 electrons are picked up by 2 silver pluses, or 2 copper pluses, right? 2 copper pluses that get reduced to the metal. Now, because we're under basic conditions, we don't make the carboxylic acid per se, we make the carboxylate. If I actually want the carboxylic acid, I would have to acidify that with HCl or sulfuric acid to get the carboxylic acid, right? In fact, many of you were doing this in your organic lab the other day. Something interesting happens though, and I'm going to sort of point that out now. When we're doing the oxidation using Jones reagent under acidic conditions, right? What do I see? Well, we've met this before, right? When I take permanganate, under acidic conditions, it gets reduced to manganese 2+. This is purple, this is manganese 7, this is colorless. Really, it's actually a very, 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 very pale pink, okay? When I'm taking chromium 6, as in dichromate, this is an orange, sort of yellow color, right? It gets reduced under acidic conditions to chromium 3+, which is green, so pretty green. When we're using the diamino silver 1 species, and that gets reduced, that makes metallic silver, right? That's silver metal. So if your test tube that you're carrying this reaction out in is relatively clean, what you see is silver depositing on the sides of the glass. So it looks like a mirror. So this is called the silver mirror reaction. And in fact, the silver mirror reaction has two values. It is a synthetic tool for oxidizing aldehydes into carboxylic acids, right? So I'm going to use MNH3 2+. So it's a synthetic tool for oxidizing aldehydes into carboxylic acids, although this would be step 1 and step 2 would be, H3O+. But it is also a qualitative test for the presence of aldehydes. Because if the compound is an aldehyde, then what I'll see in the silver, when I use the tolerance reagent is a silver mirror. If I use the diamino copper 1 species, you don't actually see a silver mirror, right? You don't see a silver mirror. What you see is you get sort of a reddish-brown sludge. You get a sort of reddish-brown, it looks like mud. It's not as, I don't know why it doesn't do the same thing as the silver. It's actually, copper is in the same group as silver in the D block. I do not know why it behaves differently. It's some microscopic feature of the atoms, I suppose. But you don't get a copper mirror. You just get a sort of reddish-brown mud. But if I see that, then the compound must have been an aldehyde. Okay? So now we know how to systematically oxidize alcohols to aldehydes, or aldehydes to carboxylic acids, and so on. And we know how to systematically reduce carboxylic acids to aldehydes, or carboxylic acids to alcohols, or whatever. Now, so there's some classic problems then that arise as a result. So I can say, what will happen if I take this compound, for example, let's see, OH. What would happen if I treat this compound with acidified permanganate? If I treat it with Tollens reagent, if I treat it with PCC in methylene chloride, what would I get? Well, in fact, let's put, okay, what would I get? Well, acidified permanganate will oxidize anybody who's oxidizable. That includes the secondary alcohol, because there's a carbonyl H here, the primary alcohol, and the aldehyde. But the secondary alcohol can only be oxidized as far as the ketone, at which point we are devoid of carbonyl H's. The aldehyde can be oxidized to carboxylic acid. The primary alcohol will go through the aldehyde into the carboxylic acid. So the product of the top reaction is the ketodiacid. Great. What about Tollens reagent? Well, Tollens reagent has no action on alcohols, but it will oxidize aldehydes to the carboxylic acid. So the product of oxidation of this compound is going to be a dihydroxy acid. What if I use PCC and methylene chloride? Well, this reagent oxidizes alcohols, primary and secondary, into corresponding carbonyl compound, right, at the aldehyde level. It will not touch aldehydes. So what I will get from that reaction would be ketone, aldehyde, and this aldehyde remains untouched. So I make a ketodiol. Now, all of these are oxidations. So if you tell me, I want you to oxidize this compound, I will have no idea what you mean. Because you could have meant a complete oxidation or selective partial oxidations. And there is great power in being able to selectively oxidize one function over the other, right? So having this arsenal of different oxidizing agents which are selective for a particular functional group is absolutely critical. And in fact, this is intro to organic chemistry. There are reagents that will oxidize only primary alcohols and not secondary, or only secondary and not primary. So the amount of degrees of freedom you have when you oxidize a molecule like this are just tremendous. Well, I can do a companion question, right? I can say, what if I gave you this compound? Right? What if I gave you this compound? And I say, what would happen if I treat that compound with LaH followed by water, or if I treat this compound with lithium aluminum tris-t-butoxyhydride followed by water, as distinct from using sodium borohydride in water. What would I get? Well, LaH is the big gun. It reduced everybody who's reducible down to the alcohol. So what I would get would be OH, OH, OH. I'd get the triol. The tris-t-butoxyhydride acts on carboxylic acids and not on ketones or aldehydes. So it will reduce the carboxylic acid function to the aldehyde. It will not touch the original aldehyde or the ketone. Sodium borohydride has no action on carboxylic acids, but it will reduce the carbonyl compounds of the aldehyde and ketone down to the corresponding alcohols. So what I would make is the dihydroxy acid. Right? This is a completely parallel problem, right? And again, you recognize the power, the potency of being able to navigate the redox ladder by choosing reagents that are specific for one function or the other. Okay? And as is the case, as I mentioned earlier, there are reagents, there are reductants that will reduce aldehydes and not ketones, others that will do ketones and not aldehydes. We will not meet those in 301, 302, right? I mean, this is intro to organic, but trust me, the world of organic is a lot richer than what we will meet in this course. Okay, let's talk now about ethers, right? So we've pretty much finished, by the way, with the chemistry of alcohols. Let's talk about ethers. And there are three things we want to talk about with ethers. Ethers obviously can either be ROR, which is what we're going to be talking about mostly. They can be RO silicon, or they can actually be they can be disilyl ethers. We're not really going to be concerned with this one at all. We only kind of mention this one as a way of protecting alcohols. We are really concerned with the typical dialkyl ether. In terms of their physical properties, ethers are slightly polar, right? They're weakly polar. Oh, that's funny. They're weakly polar. I did it again. They're weakly polar. And so they're kind of mid-range polarity, right? And ethers tend to be very volatile because they are not hydrogen bonded, right? These compounds are dipole-dipole bonded, And so all of the properties you'd expect based upon dipole-dipole bonding are obvious. They have low melting points, low boiling points, low aqueous solubilities, low viscosities, low surface tensions. They dissolve relatively non-polar compounds, although they will dissolve some polar compounds as well. Although ethers themselves do not hydrogen bond to each other, ethers will hydrogen bond, for example, to alcohols, right? Ethers will hydrogen bond to alcohols, and they will oh, good God. They will, save us, Lord. Ethers will hydrogen bond to alcohols, and ethers will hydrogen bond to water. And it's because ethers hydrogen bond to water that, for example, diethyl ether sucks up so much water, right? Diethyl ether sucks up 1 part in 7 of its volume of water, which is why if you use diethyl ether in the lab, you always have to go dry it with sodium sulfate because it actually sucks up a fair amount of water. Okay, let's look at the preparation of ethers. Right, so preparation of ethers. We will typically prepare an ether by treating a haloalkane with an alkoxide. The reaction has to be done cold, right? The reaction has to be done cold. Otherwise, the alkoxide will turn around and carry out E2 chemistry. But it should be fairly obvious that I could do this reaction in one of 2 ways, right? I could have said, why don't I use R prime O minus reacting with RCl? Because if I do it this way, I'll make exactly the same compounds. So the question is, if I'm going to make an unsymmetrical ether, which path do I use? Right? Do I use RO minus and the R prime Cl? Or do I use R prime O minus and the RCl? And the answer is, it depends upon the sizes of R. And the classic example is, suppose I wanted to make this compound. I wanted to make a methyl T-butyl ether. Well, option 1 is I could make it from T-butoxide and methyl chloride. Option 2 is I could use methoxide and T-butyl chloride. But of the 2, this is the one I will use. And why is that? Well, on the one hand, this is actually a good nucleophile, and methyl substrates can only undergo SN2. They can't do anything else. They can't do E because they only have 1 carbon, so I can't make a carbon-carbon double bond. They can't make SN1 because I can't make the primary carbocation. So the methyl substrate is doomed to SN2. So the only fate, the only role this thing can play is as a nucleophile. So the only path this reaction can follow is to make the ether. But that's not true here. Because methoxide, although it's a good nucleophile, has the capacity to carry out E reactions. And if I treat this compound with methoxide, one of the competing pathways would be to eliminate HCl and generate the corresponding alkene, which is not what I want. Now, I can't do an SN2 reaction on a tertiary substrate. I cannot. But a tertiary substrate could ionize, give rise to the carbocation, which then can react with the alkoxides, certainly to make the ether, but also to make the alkene. So I will be getting the alkene from 2 pathways. E2 on the substrate and E1 on the carbocation. The only path leading to the desired product is SN1. So I won't use the bottom approach because there are lots of, I'm going to make side products in significant yield. Okay? So when we're preparing an ether, what is typically done is I use the bulky group on the O minus. I use that as the alkoxide. And I tend to use a smaller group as the electrophile so as to encourage the SN2 reaction, because that's really what you want, right? This is called the Williamson ether synthesis. And I know I've mentioned before that the way you make an alkoxide is you simply add sodium to an alcohol, right? Alcohols react with sodium to give rise to the sodium alkoxide, right? I make the sodium alkoxide and hydrogen gas. And the alkoxide dissolves in the alcohol, and so I have my alkoxide in my matrix. So that's my preparation of the ethers. And that's the only one that you're responsible for. No, I'm sorry, there is one more, and we've met this before. I can make an ether if I start off, for example, with an alkene, and I treat that with mercuric acetate. This should be familiar. In an alcohol, followed by aqueous sodium borohydride, right? So we typically do this reaction with the mercuric acetate in water, followed by aqueous sodium borohydride to do Markovnikov hydration. But if I use the alcohol, what I'll get instead is often referred to as Markovnikov ether, okay? And so there are two methods of preparing ethers that we're responsible for. One is the Williamson synthesis, which is by far the most important of the two, the more important of the two. But the other is a throwback to the Markovnikov preparation of ethers, of alcohols. The last point we want to make about ethers is a little bit of a subtlety. If you remember, we said ethers, by virtue of their lone pairs of electrons on the O, are basic, which means ethers are acid labile, right? Acid labile. Ethers, however, do not have an acidic H, and therefore ethers are rock stable, right, in base. So if I have, for example, something like diethyl ether, and I treat that with hydroxide, there is no reaction. There's no reaction, A, because there's no acidic H, there's no H attached to O. Plus, I wouldn't have hydroxide attack the carbon because I'm going to lose the alkoxide. And alkoxide is a stronger bases than OR and OH minus, and alkoxide are terrible leaving groups. So I'm not going to get any chemistry at all. So ethers are rock stable in base. No protons are pulled off. I'm not going to have alkoxides as leaving groups. Ethers are rock stable in base. But if you remember, when we wanted to make to do hydroxylation of alkenes, we said we can treat the alkene with a per acid. That would make the oxy ring. And then we can open the ring either under acidic conditions, where the ring actually gets protonated first, right? And then a water attacks, right? And you end up with your diol, right? That was one. But we said we could open the ring under basic conditions. We had hydroxide attack, right? And if we have water in the system, so I'm going to do a second arrow, and all that means is, you just get a protonation. I make that as my product. But we just preached that ethers, and this, make no doubt about it, this is an ether, right? ROR. We just preached that ethers are rock stable in base. And why is then the base attacking it and opening the ring, right? Why is this ether base labile? Well, I'll give you a hint. If I take diethyl ether and I treat with hydroxide, there's no reaction. If I take this ether that we made by accident earlier, again, there's no reaction. If I take this one, again, there's no reaction. If I take this one, I would get a reaction if I heat it. And what I would get would be the corresponding 2, 3, 4 diol. I'll have to heat it significantly. So it becomes obvious then that as we make so acyclic ethers are rock stable. 6-membered rings, rock stable. 5-membered rings, rock stable. 4-membered rings, well, not quite so stable. 3-membered rings, they're not stable at all, right? You put them under basic conditions and they open up. So why is that? Well, I'll draw a cartoon, which is not entirely correct, but at least it gives the sense of it. You remember we keep saying that for a reaction to occur, I must climb the activation energy barrier. I don't really care where we drop, but I must climb the activation energy barrier. If there are two reagents, then their combined energies must be enough to bridge this gap. Otherwise, there's no reaction. Well, the ether, let's say this represents the energy of hydroxide. Let's say hydroxide's energy is that much, right? And I'm being kind of silly, but let's say hydroxide's energy. Well, the acyclic ethers, right, are pretty stable. Therefore, with hydroxide, we don't have enough energy to jump the hill. And this is true of the acyclic one and the six-membered ring, right? And the six-membered ring. The five-membered ring is a little bit more unstable, right? Ring strain. But the hydroxide still doesn't have enough of a wallop to give me chemistry. So I don't get chemistry. The four-membered ring is a bit more unstable, right? The hydroxide is only here, but maybe if I heat it quite significantly, that provides the rest of the energy, and over the hill we go. The three-membered ring, on the other hand, the oxyrane, is actually, while I'm here, the oxyrane is actually very unstable. Right? The oxyrane is very unstable. So my hydroxide now has enough energy to bridge the gap. So my hydroxide-oxyrane combination has enough energy to bridge the gap. So it's the inherent instability of the oxyrane that allows the reaction to go. Because if you're unstable, what does that mean? It means you're reactive. It means you're high energy. Right? And if your energy is already intrinsically high, I just have to look at you funny, and over the hill you go. So it is true that ethers in general are rock stable in base, but if we're dealing with an oxyrane, that's not just a regular ether, right? I mean, that's a highly strained reactive molecule. So it's not a surprise that oxyranes actually undergo chemistry under basic conditions, when their cousins do not. Okay, so that would end the chemistry of ethers and alcohols. Okay, what I'm going to do is I'm going to, and you guys are free to pause as you see fit. I'm just going to continue on with the next module, which is organometallic chemistry. So let's start on organometallic chemistry, right? So the lecture I just finished is one of the lectures that we were missing. Okay, remember we said we're missing 4, and I was going to do 2 this weekend. So the one so far then is the alcohol. We're just going to do the organometallic chemistry now. So organometallic chemistry, and you guys are free to pause this as you see fit. Well, as the name suggests, organometallic chemistry is the chemistry of compounds that really are hybrids between having carbons and having metals. So they basically are Rn. The nature of organic metallic compounds is really quite interesting. So the first person to sort of work on organometallic chemistry was a guy called Victor Grignard. And in fact, Grignard won the Nobel Prize for his discovery, the Grignard reagents. And the reason organometallic compounds were and are so valuable is that before Grignard had done his chemistry, alkyl groups came in 2 flavors. Either they were bound to H or other alkyl groups, like CH3 bound to CH3, right? And these had no dipole. So I'm going to write like delta 0, meaning there's no dipole. Or they were bound to things like chlorine or bromine or whatever, in which case they were delta positive. So either my alkyl groups were doomed to free radical chemistry, because the bonds were nonpolar, or they were going to be electrophiles, and that was it. But when Grignard developed organometallic chemistry, all of a sudden, the dipole switched. And the metal was now dumping electron density onto the carbon, and I made nucleophilic carbon, basic carbon. That basically allowed me then, or this is basically again, but that allowed us then to close the loop. That allowed us then a completely new set of weapons in the arsenal. Because now I could invoke not just electrophilic carbon, but nucleophilic and basic carbon. Right? And the breadth of organic chemistry just opened, it opened wide. And so it really is not a surprise that Grignard won the Nobel Prize in chemistry for it. So let's talk a little bit about the nature of those bonds. The nature of the R-M bond depends upon the metal, depends upon M. So when M is equal to sodium or potassium, the bond is ionic. So we're actually dealing with say, R minus K plus, right? So for example, I have, for example, methyl sodium is actually an ionic compound. It's crystalline. It has a high melting point. I guess it's a crystalline compound, high melting point, high boiling point. Classic organic, classic inorganic, classic crystalline behavior. Classic ionic behavior. When it's molten, it conducts electricity. Classic ionic behavior. You wouldn't put it in water, obviously, because if you put that crap in water, right, what's going to happen is it just behave as a base. You're going to get methane and hydroxide, but you're going from a very strong base to a relatively weak one. Tons of energy is released. Methane is combustible. The thing will explode, right? When the metal is lithium and magnesium, the bond is covalent, right? We actually share it, but it's highly polar. So we have R, say lithium, and the lithium is dumping lots of electron density onto the R. So I have a delta minus, 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 delta plus, plus, plus. Both of these constitute what we call hard bases, because the charge density on the R is huge. So they're hard bases. They tend to function as what we call classic bases. They pull off protons. When the metal is copper and cadmium and mercury and so on, the bond is covalent, but it's weakly polar. So I have R attached to copper, and the copper does push electrons, but that only gives me a delta minus. Okay? These are soft bases. The electron density is low, the charge density is low. These tend to function as nucleophiles, right? These tend to function as nucleophiles. These tend to function as classic bases. So it is the nature of the metal that defines the character of the R group. Okay. How do we make organometallics? Well, we've met this already, right? We can make organometallics in one of two ways. We can prepare them from haloalkanes. And we've seen this already. RCl will react with, let's say, sodium, and that's going to make the alkyl sodium, right? If I use two sodiums, I'll make sodium chloride. RCl could react with magnesium, and that's going to give the Grignard, RMgCl. This is called, oh shoot, this should not be a bond here. Right? This should just be R plus Na, R minus Na plus. This is ionic. And so this is my Grignard reagent. This is called the alkyl sodium. And of course, if I had RCl and it reacts with lithium, I would make the alkyl lithium. And that bond is covalent. Right? That's the alkyl lithium. So I could make the organometallic directly from the haloalkane. This is called umpolong. This is called umpolong, which means charge inversion. I'm flipping the charge because the carbon is going from delta plus to delta minus or minus, right? To delta minus or minus. So I can prepare the haloalkane, I can prepare the organometallic directly from the haloalkane. That's option 1. I can prepare the organometallic also from other organometallics. And we are responsible only for one method, which is the one we've seen before again in the Corey-Poisson-Whiteside house. So if I take an alkyl lithium and I treat it with cuprous iodide, I make the lithium dialkyl cuprate. Okay? If you balance the reaction, you get, lithium iodide is the other product. So I go from a hard, and this always goes that way, from hard to soft, right? So I can either make the organometallic from the haloalkane or from other organometallic compounds, and there's only one example of it for which you're responsible. All right. Let's talk about reactions of organometallic compounds. And organometallic compounds are very reactive. Well, actually, let me go one back. I could argue that there is another way of making organometallics. This would be unique to terminal alkynes. So if I had a terminal alkyne and I treated it, for example, with sodium NH2, I would lose ammonia and I would end up making the corresponding acetylate, right? And I'd lose ammonia gas. So this is actually technically an organometallic as well. Okay? So I'll just put that in. Right, so reactions of organometallics. So organometallic compounds are very reactive, and they can carry out a range of reactions, including as bases and as nucleophiles. So I'm just going to go ahead and write R minus, recognizing it doesn't necessarily have to be a standalone anion, right? So this R minus may well be R delta minus, as in a cuprate, or maybe R delta minus 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 minus, as in a Grignard or an alkyl lithium, right? Or it could be a standalone R minus, as with an alkyl sodium or an alkyl potassium. So I'm just saying R minus, I'm going to put it in quotation marks. They are capable of a range of reactions, and I'm just going to put some arbitrary number of arrows. There may be more than these or less, but these are what it gives. Well, certainly, they react with haloalkanes, right? And they'll give me R prime. This is the Corey-Poisson-Whiteside house reaction. And all the things we've said about it will be true. This R prime X would have to be methyl, primary or secondary. And the R would have to be, this would have to be a cuprate, right? So this would have to be for a cuprate, right? So we couldn't do it if it were not a cuprate. They also react, and we've seen this already, with carbonyl compounds. We did that today. Or we did that recently. So they react with carbonyl compounds. And what they will generate would be R, right? So carbonyl compounds followed by water would generate the corresponding alcohol. They react with esters. We saw that as well. Right, so I'm gonna lots of R's here. So I'm gonna put R prime, R double prime. They react with esters followed by water, and they generate R prime, OH, R, as well as R double prime, OH. We spent a lot of time on that one today. They react with oxyranes, followed by water, and they generate R, OH. And these are fairly standard reactions, right? The oxyrane one, we may not have actually talked about it in detail, but you can imagine this would simply be an SN2 reaction. The ring would open, and you end up with your alkoxide which reacts with water, and you pull the proton off, and you have your product. They react with terminal alkynes to generate the corresponding acetylide. And let's see, what else am I missing? So carbonyl. I have a feeling I'm missing one. So haloalkanes, carbonyls, esters, oxiranes, alkynes. Okay, I'm gonna say that's it. The ones that were responsible for it. I think that would pretty much do it. Okay, and in fact there are actually a few. Well, maybe not. There are a few others that we can do, but they're probably a bit more on the exotic side. So I'll probably just leave those out anyway. Okay. So, and in fact, let me just say, they will react with anything that has an X double bond Y or an X triple bond Y, where there is a polarity in the molecule, right? So there's a delta plus and a delta minus. So they react with nitriles, they react with nitrosyl compounds, they react with thionyl compounds, and so on. So anything with that sort of group, not surprisingly, they will tend to give chemistry with. But I'm going to kind of put these in a square bracket. Because the ones that we have here are by far the most common of the reactions that we're responsible for anyway. Let's talk a little bit about the limitations, in the preparation of organometallics. Okay, and actually, before I do that, I do want to point out, because I kind of glossed over it a little bit. We spent a lot of time on the Corey-Poisson-Whitehead-House reaction. You want to remember that when we're doing Corey-Poisson-Whitehead-House, I convert the alkyl lithium into the cuprate. I soften the base, because hard bases like the alkyl lithiums tend to carry out proton transfer. When the base is soft, like the cuprate, it tends to attack carbons, right? So we've harped on that before, just to make sure we have that. So there are a few limitations in the preparation of an organometallic, and it is not terribly surprising. If the compound that you're preparing the organometallic in or from contains, if it's polyfunctional, and it contains another group that is either acidic or electrophilic, then we're going to have a problem. For example, suppose I start off with one of the molecule we had somewhat earlier, and I want to make the organometallic compound from that. So I'm going to say, let me go ahead and treat this thing with, well, that would be a very bad idea, but whatever. Let's say I'm going to treat this compound with sodium. My idea would be, or let's say lithium. My idea would be I would do umpalong at this site and try to make this compound. Right? 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yeah, wait. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So I wanted to make then is the alkyl lithium. Well, that's just very exciting. So I want to make the alkyl lithium. Now, for a couple of other reasons, that'll be a problem. But anyway, so let's press on what I'm doing. One of the big problems here is, if my intent was to use this alkyl lithium to do some chemistry outside the molecule, maybe act as a base or I don't know, whatever, I would fail abysmally, because built into this molecule is an acidic proton. And as we said, proton transfer is the fastest reaction in organic chemistry. Can you imagine how fast that would be if the proton and the base were in the same molecule, right? Reactions normally take a certain measure of time because the two reagents are swimming towards each other in solution. They're moving in solution. They have to find each other in solution. They must collide in the correct orientation with enough energy to jump the energy barrier. Well, if the two sites, the base and the acid, are in the same molecule, there is no finding. They're built into the same molecule. They're in the same house. Heck, they're in the same room. So that reaction is blindingly fast. So long before this species waits to find some other reagent, it's going to target this species, right? Basically, what will happen is I'll pull off the proton and make the alkoxide, and we'll end up with this species. And why that's really bad is that if you then treat this with some electrophile, let's say you're treating it, I don't know, with say methyl chloride. Your hope would have been that the lithium, because methyl chloride, of course, can't do E, right? So your hope would have been you'd have made this compound. So I'll put a methyl, my new methyl group would be here, and I would have had this product. You're not going to get that. What you're going to get is this one, right? Because that will attack the methyl. And what's really weird is that these two are isomers. And if all you had done was measure the molecular mass, for example, you would get exactly the same molecular mass. And you would say, well, whoopee, I made this compound. When in fact you didn't, you made that one. The problem is you made an organometallic in a molecule containing an acidic H. And if your intent is to use the organometallic intermolecularly, it will fail. If, for example, you take, you have this compound, and I treat that with magnesium, hoping to make the Grignard, right? So I make the magnesium chloride. If my intent again is to use this Grignard to do chemistry on some electrophile outside the molecule, that's not going to happen. Long before this finds that, it will find that, right? So it's going to attack the electrophile that's built in, and I'll make a 1, 2, 3, 4-membered ring. I'll make a 4-membered ring with an O- on it. Okay? So if your molecule has any electrophile, and what do we mean by electrophile? Anything from a carbon-halogen bond, right? Anything with an X double bond Y, right? Any X double bond Y would be an electrophile. An oxirane would be an electrophile, and so on. Anything that's acidic. And how acidic do you have to be? Well, think it through, right? Let's think that through. You simply have to be more acidic than an alkane, right? Because what we're doing here is we're having the R- pull off the proton. The proton goes onto the carbon, and I end up, in fact, there should be an H. I end up with a corresponding alkane. The strong acid gives a weak acid. So who is stronger as an acid than an alkane? And the answer is everybody, right? Alkynes, terminal alkynes certainly, alcohols, thiols, etc., etc., etc. So you have to be very careful as to what other functional groups are present in the molecule. Because if they are as acidic as an alkyne or more, God forbid OH or God forbid carboxylic acid, or if they are electrophiles, and there are a whole slew of them, right, from our menu, right, a whole slew, haloalkanes, carbonyls, esters, oxiranes, and then I mentioned, you know, nitriles, nitroso, iminilyl, any of that thing, then the Grignard, the organometallic, will turn around and attack it. And you would have quenched your organic, you would have quenched your organometallic compound. Okay, so that would end our discussion on organometallic chemistry. And I would call this lecture, that would be the end of this lecture. So at this point then we finished module 3 and module 4. We'll stop here and pick up in class on Monday. Okay, we'll pick up in class on module 5. Okay.